So first, let me explain why there are two names on the slides and it's only me. Unfortunately, Alec couldn't make it, so I have to do his half of the talk as well. And my name is Łukasz, and I indeed work for Google on the Android malware research team. So today I will talk to you about OTA apps, not OTA updates. So I will start with what are the OTA apps and how they can be abused by the malware authors. I will then show you two real-world cases where they were abused by the malware authors. And at the end, I will tell you how we combat that kind of abuse and what we do to prevent it. And if we have some time left for questions, I'm happy to answer them as well. So the first thing is, what are the OTA apps and what do they do? So the core functionality of the OTA app is relatively simple. They do all the admin tasks of getting the OTA on the device. So they check whether the OTA is available, whether there's a new version that is compared to the version that you have. They handle the downloading, they handle the things that you may ordinarily expect, like delaying it until you're on a Wi-Fi or these kinds of functionalities, and then they pass over the whole system image to the Android API, and Android makes sure that it's properly signed, then handles the update process, the reboot, and all that. So they only do the admin task. So there's nothing that influences the OTA system image in the app itself. The problem, or rather the abuse vector, comes from additional functionality that these apps implement. So the additional functionality is something that the device manufacturer may want. So they may want to have a lightweight system update. That means that if they want to update a system app that's on your device and they just want to update this one system app, it doesn't make sense to send you the whole system image, because then you will have to go through the reboot process and it takes time and it's not very user-friendly. So they may send this one app and install the app, or they may send an additional app and install it to enhance the user experience. Or they may have a configuration change, which also doesn't require your phone to be rebooted or the system image to be changed. So this additional functionality that is added to some of the OTA apps is where we can find the potential for abuse. The OTA part is safe. And in Android, you almost always have multiple parties involved. So I already told you that there are device manufacturers. There are, of course, third-party providers. So for example, if the OEM it doesn't have a software team, they may ask some subcontractor to do the OTA app for them. They may buy it from a different place. They may write it themselves. They may use Google OTA. We also have the OTA app. So there are many, many different components before the decision is being made. So there are many different sources of these OTA apps, and this is one of the targets for abuse. So they may be, the app itself may be contracted to a vendor and may come from an untrusted source, and then you may have to check whether the app is safe and secure. These apps usually also have sensitive permissions. As you can imagine, the OTA app has to do a number of things on Android that are considered privileged. So it may install other apps. Obviously, it may reboot the phone, and fairly often it runs as a system user. So it has even more elevated privileges. And then can access some hidden framework APIs and share permissions with other system apps. So every app that runs as a system user has the same superset of permissions. And as I mentioned, they also download the apps. So this is for the purpose of updating the apps that you already have on your phone, a lightweight update, or installing a new app that will in some way enhance the user experience. And you don't know what apps they will download until they will download the apps, obviously, because that's all handled server side. So these downloads have to be watched closely to make sure that what's downloaded is actually non-malicious and a benign app. So now I will move on to two real-world case studies. One of them was done by Alec, so I'm presenting his work. I want to make sure that you are all aware of that. And also, if I make any mistakes, it's all his fault. So the first one is is an OTA app that downloaded additional apps that weren't so benign. They were malicious apps. And it was in the news 2 times, or at least we were able to find it 2 times. Once was in a blog post by Malwarebytes, and once was in a blog on Ninja's website, that had all the technical details about this app. We were able to find the second version of this app. Obviously, when we detected the first version, they moved on to the second version, and I will elaborate slightly more on that, and I will also tell you what apps were downloaded by this OTA. So the way the app worked is the classes.dex file contained the code to actually do the OTA and do all the downloads and all that stuff, and that code was in Java. And there was a second part that was written in Lua, and it had workers. Workers were basically kind of Lua plugins, or whatever you want to call them. And the first version of the app that came with the phone only had a very simple worker that checked in with the server and downloaded more stuff, or upgraded itself to a more complex version that had other capabilities. So the kind of the work cycle was to check in with the server, get the command from the server, update itself, and execute the command and go in circles like that. And this is almost always the case in every OTA app that we've seen that had this additional functionality of downloading malware, that there are these 2 worlds. One is this clean code written in with proper class names and whatnot, and this is the code responsible for the actual OTA. So downloading the system, I mentioned all that. And there's a second world that is usually obfuscated or somewhere else, or dynamically loaded, or whatever, and this is the code that's responsible for malware downloads. So one of the ways you can see that the OTA app may be malicious is that it will have 2 separate code paths for app downloads and installs. One is the one that it should have, and the other one is the one that is additional and will download malware. So this is the example of the upgrade command that was sent to the CNC and was used to upgrade that Lua worker to one with more capabilities. The interesting thing you can see is the URL here. So they are definitely trying to look legitimate, and you have to look closely to know that that URL is not really the URL of a very popular social media website. And they use also very similar URLs. I don't know if this is as a joke or to actually hide in the network traffic. So they also used something that looks legit in the network traffic. And as I said, the response to this was to send more Lua workers that were either downloading apps or doing something else. Everything here was XORed. Obviously, that's the best form of encryption, isn't it? So just to make sure that it's harder to track the traffic. And you can see the code here that was used to not only download, but also launch apps. So when you download and install app, any new app, user has to click on the app icon for it to actually run. Or the software that downloads it, in this case OTA, may have permissions to run it for the user. But if you just install the app, nothing will happen. So they also have to make sure that the app is run in addition to being downloaded. And one of the plugins was used for ad fraud. So it loaded plugins dynamically that were linked to known ad fraud families, known kind of big ad fraud botnets that we talked about before. There were usually no user-facing components or launcher activities. Obviously, the purpose of everything was to run in the background and not to alert the user. And here's some example of the code that they used to perform ad fraud. So this one was to scroll the website. And you can see a lot of randomness. Randomness is always set in any ad fraud kind of apps to make sure they simulate the user better, right? So if they will click on every single ad at the same exact point, usually at the center of the ad, it's fairly easy to detect that kind of behavior. If they do it randomly, they think it's harder to detect them. And this is another example of, again, this is a random click, but the randomness of the click only comes to the clicking time, not actually where the click is done, and it will click on every A element on the website in any random click time between 4 and 6 seconds. I think that's it. That's that. Interestingly, this particular OTA also used a system-level backdoor. So there was the system service. This is the name for the system service. And its purpose was to export the Android API so that they can be used without any permissions. So this was a system service that ran as part of the operating system, and it allowed to install and uninstall APKs and set component enabled and all this stuff that is mentioned here. Obviously, the service didn't provide any kind of authentication, so not only the OTA app, but also any app on the device that was able to detect this service could use the same kind of access to the device without any permissions. This is obviously a vulnerability, and this was disclosed through our APVI program, which deals with vulnerabilities found in additional code, the code that's not part of AOSP but still is shipped with the device. And under this link, you can see the details of the vulnerability. It was disclosed to the partners, and they fixed it, so it's no longer present on user devices, or should be no longer present on user devices. And after we started detecting version 1, and I will tell you at the end what I mean by detecting, because it's a very kind of particular way of detecting OTA apps. They returned with version 2. Version 2, the theme for version 2 was obfuscation. So they introduced a lot of obfuscation in order to make it harder to detect, presumably. The first thing is that they moved all the malicious code outside of the app, and they used an existing ELF binary that is on the system image to put all the malicious code in as native methods. So the app itself only had references to native methods, and these native methods were in a system library. In this case, this is the name of the system library that they used. So if you had the APK file itself, you wouldn't know what it does because you didn't have that system library next to it. It was just part of the system. They also did a lot of detection of debugging tools and emulators. You can see some examples here. So if you have like logcat running or whatever, they wouldn't even continue with the execution. And this is done before any actual code is loaded, right? So if they detect something, they will simply start working. Same for emulators. So you can see here they detected some of the emulators. And if they detected that they were running in an emulator, they would stop running. And then if all these checks have passed, so they are sure that they are running on the right device because it has that ELF file that they've modified, it's not an emulator, it's not a debugger, it's not whatever, then they will move on to oh, sorry, there's one more check. The one additional check is for exposed. So if you have an instrumented emulator and you use exposed to instrument them, as some of the dynamic evaluation environments do, they will also detect this and stop running. So after this one additional check, they will unpack the code that is used to install and download and install apps, and they will also drop an additional DEX file to the Dalvik cache location. And again, same story, Lua workers, they send a ping to the CNC, upgrade themselves. There's a Lua worker that downloads and installs apps and so on and so forth. So this is the first case study. Oh, and I forgot to mention, of course, everything is XOR encrypted with 1 byte key, obviously. It has to be. Otherwise, it wouldn't count as malware. So the second case study is for a different OTA app. And this one also came in different versions. So whenever we detect something, they switch to a new version. When we detect a new version, they switch over to the next one. And this one was only mentioned once, or at least I found it mentioned once during Google search. So if someone did mention that, I'm sorry I didn't include you. But again, Malwarebytes did a blog post about that. This part of the talk will also show you the newer versions and what the OTA actually downloaded. So the first version was fairly simple. You can see on the top right here that it had a jar file. These numbers in the jar file are the version of the jar file. So then it contacted the CNC and said, this is the version that I have. Do you have a newer version? It downloaded a newer version and ran with that. So this was the kind of a default version. And then if it wanted to upgrade it, did that through the CNC. And there were two interesting features in this version. So the first one was the opportunistic use of SU, and that is something that I fairly often see in Android malware. If you have an SU binary that is not protected in any way, malware will try to use it. Obviously, it wants to get higher privileges. So if your phone is rooted and you have an SU binary, you may want to check whether it's properly secured for the malware use. And the second feature was the complete and utter lack of any TLS certificate validation. So you could substitute it with any other TLS certificate. It didn't matter whether it was signed or not. All the errors were ignored. Then, when we started detecting this version, they moved on to the second one, and this second one shows you the additional classes with obfuscated names. So the names are in Unicode, and if you have, if your reverse engineering tool doesn't handle Unicode class names, you will see something similar to this. So obviously, the code is now slightly more obfuscated. The one in the jar file really wasn't that obfuscated; it was just separate. And you can see that there's an app dropper here. So this one works of intents. You can send it a download URL and a package name version. And also a couple of additional things are class name and action and start KV. This is to make sure that the app is running. Again, if you install the app, you have to either click on it or somehow make it run. So they included the class name and action to start the app with a proper class name and action that they wanted. And V2 features, again, the theme for this one was obfuscation, much like for the previous V2 in a separate case. So encoded CNC URLs, base64 encoded. If you're familiar with if you did a lot of base64 encoding, you may notice that the beginning spells HTTP. And then, as I mentioned, it starts activities using AM start. So again, just to make sure that everything is running in the background. And they ported the most important feature from V1, which is, again, a total and utter lack of any TLS validation between the app and the CNC server, so ignoring all the errors. V3 was slightly more interesting because they came up with their own file format. It's not a very complex file format, but it's still a file format. So it starts with a magic header, and that is either cordex1 or cordex2, depending on the version. Then you have 4 bytes of the file size, and then you have the XORT APK. And now the XOR key, interestingly, is different in different versions, and different in different versions of the app. I'm not sure how they make sure that the app is correctly unXORed with the key, but it's just a 1-byte XOR key. And as I mentioned, you always have to have XOR encoding, otherwise it doesn't count as malware. And you can see on the left here that they also used Unicode class names. Here I left it so that you know that our reverse engineering tools can handle Unicode class names and render them properly. And you can see that once it was unXORed, it contained classes.dex and manifest.mf. And the unXORed file, interestingly, was not very obfuscated. They did some class name stripping and like method name stripping, but I don't know whether that's a software development practice, like you want to make sure your DEX is kind of compact and smaller, or whether that's an obfuscation thing. I assume that if they went with the obfuscation route, they would use something like Unicode characters again, just to be consistent with that. Okay, so this is the CNC response that we were able to find. This shows you what types of apps they were distributing, right? This is not the actual URLs that were used to download the apps. This is response to make sure that the apps are running. So we will have which class will be run for any app just to make sure that the app is constantly running. But it shows you that this app controls all these other apps. So by now you probably have a question, what are these other apps? So again, this is in a very, very broad sense, ad fraud. It's click fraud, it's advertising spam, hidden advertisements, so something that you won't see, but will still count as an impression, I guess. And disruptive advertising, which means out of place ads when you don't expect them. And again, the click fraud here is slightly more randomized. So they not only randomize the time, but they also randomize the pressure of the click, the position of the click, and all the other stuff is random to make sure that it looks more like user input rather than something that was automatically generated. And here are some tricks from the actual payload. So this is not from the OTA. This is from the apps that were downloaded by this malicious OTA. So on the upper right-hand side, you can see that one of the apps had an icon. And this icon is not only an icon. It's a PNG file that contains a jar file. And that jar file is XOR encrypted with a 1-byte key that is also hidden in that PNG file, which is pretty amazing, isn't it? It's just an icon. And again, XOR encryption, otherwise you can have malware, really. The other thing it did is it kept counters for different ad services. So a very generous interpretation would be that they didn't want to spam the user with ads too often. A less generous interpretation would be that if they did it too often, it would probably be easy to detect server-side that they requested too many ads for any sensible app. But my favorite one is the one on the left that shows you how not to get the top activity. Let's go through it fairly quickly. So this was a loop that was running constantly every so often. And it paused the PS command to get all the processes that were running. And it diffed that with the previous one. So it was not interested in the processes that were already running during the previous iteration, right? It was only interested in new processes. And then it removed the processes that had the name not starting with com dot. So it was only interested in processes that were starting with com dot something. So it assumed that all of the interesting Android apps will have a name, package name starting with com dot something. Then it did a bit more filtering. It removed the processes that it was not interested in. This was a list that was both hard-coded but also updatable from CNC. So after all that filtering and removing all of the uninteresting processes, it took the one with the highest process ID as the activity that was running in the foreground. It has to do all of that because getting foreground activity on any new Android is very difficult. So it tried doing that, and if you think about it for maybe 2 minutes, you can figure out multiple edge cases in which it won't be the top activity that they were looking for. Also, the PS process doesn't really, or the PS command doesn't really work that way on new versions of Android anymore. Okay, so finally, last couple of minutes, I will tell you what I meant through the whole talk when I said detection and how we combat that. So obviously, you cannot remove the OTA app from user devices because users won't get the OTAs, which is super important for the users. This is also why it's a particularly interesting abuse vector, right? Because the attackers know that the OTA app has to stay on the device. So whenever there is a new device being released with Google Apps on them, it has to go through a number of tests. And these are fairly comprehensive tests. They cover compatibility aspects, so something that is probably not interesting for the audience here, but is very important for the users, up to security aspects like vulnerabilities, patches, and also malware scanning. In particular, BTS, Build Test Suite, is the one that we run on system images to make sure that that there are no malware apps, and it runs on the whole system image. So the apps are scanned, but also all the other binaries are scanned. So I've mentioned a few binaries that were used, right, by these OTA apps or like system services. This is all part of the system image, so the BTS scanning process makes sure to take this into account. And then the device is either approved or it's not. If it's not approved, the system image has to change, and the malware has to be removed in this case that we are talking about. And finally, some stats for you. So in 2021, last calendar year, we've scanned more than 3.4 million pre-installed applications. This is only the applications, and they were scanned on over 100,000 system images during the whole year. So as I said, apps are just one part of it. The whole system image is scanned, including the binaries that are not in apps. Okay, so this is everything. Thank you for listening. Go follow Alec, even though he's not here. Go follow him on Twitter. He did a lot of research that I've presented here. And this is my Twitter handle, so you can also follow me. And thank you. And if you have any questions, I think we have some time to answer them. Yep.
Yeah, thank you, Łukasz. Do we have any questions? There's one question over there. Wait for the microphone, because otherwise we will not hear you.
Hi, Łukasz. Can you hear me?
Hey, yes.
So you said that these malicious OTA apps were ignoring TLS error messages. Does that mean it's easier to machine in the middle them and sniff the traffic?
Yeah, kind of. But this is only, or I don't know if it makes it any better, but this is only about the CNC communication. It's not about the OTA communication, which was done through a different set of source code. Does that make sense? Okay, yeah.
Any further questions? This one right over there.
Are you able to reveal the device manufacturers, which obviously have allowed these things to be pre-installed?
I don't remember them, but it's not limited to like one particular one, if that helps. It's again, due to the way that the supply chain is set up, they were just subcontracting into a third party, and then that third party turned out to provide malicious code, right?
We still have time for a couple more questions. There's one way back there.
Hi, awesome talk. Just wanted to ask, what's the recourse for the user if they end up with a device that has an OTA that downloads malware?
Install updates. Because when we work with the OEMs, I forgot to mention that. That's a very good question to mention that. We also reach out to OEMs to ask them to update the devices that already have malware in the wild. So it's not only that we scan the devices before they hit the market, we also do scan them once they are out. And the OEMs will provide a system update for malware discovered that way. So the request for the user is make sure you have your phone is up to date.
We have one more question there. I think then we have to, well, we'll see how long it takes. Let's see.
Are there certain firmware over-the-air service providers that OEMs use that you notice tend to push out malicious OTA updates more often than others? And if so, do you or can you scrutinize those providers a bit more than others?
So again, this is not about the OTA updates. OTA updates are just provided through their infrastructure. But the whole process of providing the OTA update is safe and secure. And this is a separate thing with the additional code that was separate from the code that handled the OTA update. So to answer your questions, they cannot really interfere with that because the OTA system image is signed. They just use the fact that you have the OTA app to put some additional code to it that will download apps.
Any really, really quick questions? Because we're basically out of time. If not, then thank you very much, Łukasz.